Hi, today we are going to discuss about thin film deposition. Deposition is to grow some material on the silicon substrate. Uh, we use uh, we use two kinds of deposition process. First, we can use chemical vapor deposition system. We use chemical reaction for deposition. On another way is the physical vapor deposition. This we in this way we use the physical reaction for deposition. Deposition can be used for grow materials such as metals or dielectrics. First, I'm going to discuss about the growth model. Uh, growing materials looks like the growing a thin layer on the atoms. However, for some reasons, such as the poor chemistry, such as the affinities between the materials. Some materials can be grown from the grown like the island model and grow like the 3D island model. Moreover, we can for some reasons such as thermals, uh, the growing materials and so on. We, the growing materials can be made into epitaxial or crystalline structure or polycrystalline or amorphous. Next, we're going to move on to the stack coverage or conformer coverage. Conformer coverage is, as you can see here, is to cover the surface uniformly. On the other hand, non-conformer materials can be covered to close the hole. Normally, conformal deposition is preferred. However, for some reasons, we if we need to if we are supposed to close the hole, such as such as the dielectric coverage, we can use this non-conformer coverage. This is this is the this is one example why we need the poor stack coverage intently. We can make this void between these structure to to cut the cut the structures from the uh, capacitively coupled. Let's move on to the chemical vapor deposition in uh, deposition more. Uh, just like the etching process, the chemical vapor deposition consists of three steps. First, we introduce the gas. Next, react the gas with substrate, and last but not least, remove the byproduct with the gases with in gas. If the byproduct is not gas, the byproduct can be deposited unintentionally to cover of the surface. There are some kinds of CVD systems here. First, there is atmospheric pressure reactor. We use heat and gas to deposit the wafers, but because it is because it is tend to be contaminated really easily, so it is not uh, industrially used. However, industrially, uh, this low pressure CVD or the plasma enhanced CVD is relatively widely used. First, we can use the plasma to enhance the growing, or we can make this low pressure chamber to and bake the and make the materials less scattered to grow uniformly. Nowadays, in this semiconductor field, atomic layer deposition or ALD is widely used because in this technology we can grow the layers in atomic layers, and we can even the and it can and we can even the bake layers, multiple layers chemically with different materials. In this ALD in these ALD technologies, a lot of modern semiconductors, especially for 3D structures, can be made. Next, we are going to discuss about physical vapor deposition. Unlike chemical vapor deposition, uh, we only use physical reactions to make vapors such as heat, electron beam, and so on. First, let's move on to the evaporation. In this method, we can use heat or electron beam to make the materials to evaporate. In this heat evaporation, we only use single materials. However, in E-beam evaporation process, we can put multiple materials and select the materials in one time to evaporate. However, in this evaporation system, there is a problem with step coverage, because the vapor tends to move in one direction. So in 3D structures, there can be uh, this shadowed region. Next, there is another way to make vapor sputtering. We put the argon or this uh, in this 18th family materials gas materials, and make the gas into such as a plasma like type, and sputter to this target. The sputtered target is transformed into is turned like into like nano bubble or something, and this is deposited because the sputtered target tends to move in many ways, so the coverage is really so the conformity is really good. Last but not least, we can even use post-laser deposition. We use laser beam into in pulse, and because the pulsing laser has a lot of energy, the target can be easily evaporated. Last but not least, there is molecular beam epitaxy. We can use multiple heating coils and multiple products to select the materials and evaporate like the two bakes such as this ALD-like structures, or even chemically react with, or if we open some multiple materials in one time, we can even use uh, these uh, these chemical structures. However, this molecular beam epitaxy is extremely expensive, so it is only used it is nearly only used in laboratory. Thank you for listening.